is this problem? Metin, where are you, Metin?
What's wrong, Zindamon?
I'm so glad you came. Actually, there's this problem.
This is... I understand it now.
Ka! What do you mean?
This is a kind of differentiation.
Differentiation? Isn't differentiation
Yeah,
supposed
like
to be
that.
like this?
Yes, that's certainly what is
Or
commonly
could,
known as differentiation.
But the earlier
X
problem
to
looked
the
like
power
this.
of a half.
For some reason,
Doesn't
the
work like
dx
that.
part was replaced with d square root x.
Yeah, that's bad.
This means it's like differentiating with respect to the square root of x instead of
That
x.
makes sense.
What does it mean to differentiate with
substitute.
respect to the
Just
square root of
substitute
x? I
square
don't
root
understand what
for,
you're saying.
E.
Alright then, let's figure out what this
Q.
is together.
Ah, yeah, please help me.
Suppose we have a graph of y equals f of x on a plane. And let's plot the point at x, f of x. And the point at x plus h, f of x plus h, like this. What would be the slope of the line passing through these 2 points?
Tangent.
The change in the x direction between these 2
Yeah,
points
that's
is
the
x plus
definition
h
for,
minus x. And
Limit
the change in the
definition
y direction is f of
for
x
diff-
plus h minus f of x. So
or
this would be the
derivative.
slope
Yeah,
of
that
the
was-
line,
that's what I
right?
was trying to say.
Exactly. The denominator is essentially just h. But for now, let's leave it in this form. Okay, regarding the slope of that line, let's consider the limit as h approaches 0. This is called the
go.
derivative of f. And finding the derivative is what we call differentiating f. Usually, we just
Yeah,
write
that's
the
definition of
denominator
the
as h.
derivative.
Oh, right, I remember that.
Mhm.
So differentiation is about finding the slope of the tangent at
Yes.
x.
That's correct. So
Exactly.
then, based on this definition of differentiation, can you define the expression that appeared earlier?
Hmm.
You
In the
just
usual
substitute.
differentiation notation, the denominator is dx. This represents a small change in x. On the other hand, this one has d square root x in the denominator. So, does this represent a small change in the square root of x?
Sharp observation.
Today, no one can stop me. In usual differentiation, a small change in x is expressed in the denominator like this. So, in this differentiation, we should represent the small change in the square root of x like this.
Wonderful, Sundamon.
Exactly.
With this, we have to find the operation of differentiating with respect to the square root of x instead of x.
This is such a strange definition.
Here, let's remember that the square root can be represented as the half power. More generally, if we take alpha as a positive number, the differentiation of f of x with respect to x to the power of alpha can be defined like this. The earlier definition can be considered as the case where alpha equals 1/2.
This is. Instead of a small change in x, a small change in x to the power of alpha appears in the denominator.
It can get complicated when imaginary numbers are involved, so let's assume x is greater than or equal to 0. Technically, we are using a limit here. And if x equals 0, we would need to let h approach 0 from the positive side. But let's leave that aside for now.
I don't really get it, but let's just
I
leave it
assume
for
it
now.
works similar.
Here, if we
Let's
consider the
compare
case where
negative
alpha
number.
equals 1 with this definition, we should be able to confirm that this matches the usual differentiation.
Indeed. In that sense, this definition is a generalization of the usual differentiation?
That's one way to think about it.
By the way, I feel like I've seen this symbol somewhere before. Oh, I remember. There was a symbol representing the nth order differentiation, which means differentiating n times. Is this different from the symbol we defined this time?
That's definitely something to wonder about. In conclusion, although they look similar, it seems best to consider them different. This dxn can be thought of as dx to the power
And
of
it
n.
has to be an integer.
In other words, it's
A
treating
alpha
dx as if
isn't.
it were a single variable. But in the case of dx to the alpha, it represents the small change in x to the alpha, so d only appears once. At least, that's what I think, but please leave a comment if I'm wrong.
You're sounding a bit unsure.
Alright, Zundamon, try calculating this as an example.
I'll do it. We're differentiating x with respect to the square root of x. Well, first, let's represent it using the limit according to the definition. Then, we write the change in x in the numerator. And the change in the square root of x in the denominator.
And then you
The numerator
square.
is just h, so it looks like this.
You square top and
To
bottom,
eliminate the square root in the denominator for
which
now.
is 0.
let's multiply both the numerator and denominator
this
by this
one
expression.
Trying to do exactly like
Then
this.
the denominator becomes like this.
Then you have
And
0.
it seems like the numerator can stay as it is. Now, since the denominator is just h, the h in the numerator and denominator cancel each other out.
You get
Then,
2x
if
squared.
we let h approach 0 in this expression,
Or,
the answer is 2 square root x.
Yeah.
Well done, Sundamoon. In summary, differentiating x with respect to the square root of x gives this result.
This is also an equality I'm not very familiar with. But, somehow, I feel like I've seen it somewhere before. Why is that?
That feeling is probably not wrong. Because, as an alternative solution, if we let y equals the square root of x, this expression can be rewritten like this.
Wow! It's just a regular differentiation problem. If we differentiate y squared with respect to y, it becomes 2y. So the answer is 2 square root x.
Yes, exactly. However, this one is differentiated with respect to the square root of x as defined earlier, while the other is the usual differentiation. Technically, we need to verify the validity of this equality based on each definition.
It's fine. I understand it. By the way, I've just had a realization.
Wait,
so
what is it?
Let's reconsider differentiating.
I was right, you have to substitute. It's just because you have a different definition, you do it in a different way, you need to be extra careful here, right?
F with respect to x to the alpha. Here, imagine the differentiation of a composite function. Treat this differentiation symbol as if it were a fraction, and manipulate it like this.
What did you say?
Something's off with Nuttin. Let's continue. Now, let's change this from multiplication to division, and flip the numerator and denominator. Then, since we're simply differentiating x to the alpha with respect to x here, we can calculate it like this.
I see, this is interesting. In this expression, only the usual meaning of differentiation remains. In other words, the differentiation with respect to x to the alpha has been reduced to usual differentiation. But we haven't yet verified the validity of the manipulation used here. It certainly seems like we could interpret it similarly to the differentiation of composite functions, but just to be sure, let's verify this calculation according to the definition.
Oh, yes. Then let's proceed with the calculation according to the definition. The differentiation with respect to x to the alpha was defined like this. Here, let's transform it like this to create the usual differentiation. Then, change this from multiplication to division, and flip the numerator and denominator. Okay, this becomes the usual differentiation. And here we're differentiating x to the alpha with respect to x. So the answer still comes out like this.
That certainly seems correct. We have to be careful if the denominator becomes 0 here, though. So, it turns out that there is this relationship between differentiation with respect to x to the alpha and the usual differentiation.
It's a beautiful formula.
For example, if we consider f of x equals x to the beta, we would differentiate x to the beta with respect to x to the alpha. We take the denominator directly from the formula, and then differentiate f in the usual sense, which means we differentiate x to the beta with respect to x, and it becomes like this. Simplifying, we get this result.
This is quite an interesting result.
Now, if we substitute alpha equals 1, this turns into the familiar power rule for differentiation.
Oh, that's true. So this equality is actually a generalization of the power rule. By the way, I've been thinking, if differentiation with respect to x to the alpha can be expressed using the usual differentiation, then from now on, we can just use this formula, and we wouldn't need to use the definition of differentiation with respect to x to the alpha anymore, right?
That's a reasonable thought. But, I'd like you to think about this for a moment. For example, take the function f of x equals the square root of x. And let's differentiate it with respect to the square root of x. Skipping some intermediate steps, but if we calculate it based on the definition, we find that the result is 1.
Well, it does seem like that would be the result just from looking at the expression.
On the other hand, if we differentiate f in the usual sense, the result is 1 over 2 square root x. However, as you can see from the denominator having the square root of x, f cannot be differentiated at x equals 0, even from one side.
Oh, that's true. Whereas in this case, it's clearly differentiable at x equals 0.
In other words, even if a function is differentiable with respect to x to the alpha, it may not be differentiable with respect to x. So there are cases where this formula alone cannot apply.
Differentiating with respect to x to the alpha seems harder than with respect to x, but it's kind of mysterious.
Actually, the differentiation we've discussed today is called fractal differentiation, and it's said to be an important concept in the field of fractal geometry.
What? I didn't know that.
Fractal differentiation has properties similar to usual differentiation. For example, the sum rule for differentiation also holds for fractal differentiation.
The sum rule means we can calculate the derivative of a sum as the sum of derivatives.
Similarly, the product rule for differentiation also holds for fractal differentiation.
Oh, really?
What are the
I think this is also called Leibniz rule.
quotient rule?
This makes the calculations much easier. Fractal differentiation.
Hey,
It's not something to underestimate. Oh, it's about time we wrap things up.
Well then,
Does it
take
hold?
care everyone.
See you
quotient- I
again.
assume quotient holds too. Is it just a specific it's a specific situation for the product rule, I think. Wow. My brain is expanding.